Hey, I'm back and I'm returning to my fifth video on examples with KVL and KCL applications to circuits. So let me go ahead and draw out a circuit. Okay, here we go. And if you notice, wow, this time I'm actually going to use some resistors in this circuit rather than just generic circuit elements. I felt like it's about time I start doing this so you get used to working with a real circuit element and you can get a feel for what's actually a source, what's actually passive, and where power is consumed and where power is generated in this circuit. And I just want to get us a little bit more involved here. So this is the scenario. We have 5 elements in this circuit, one source labeled Vs, it's a voltage source, a 5 ohm resistor here, and then 3 resistors, if you notice they're in parallel, 10, 5, and 5 ohms. And then one piece of information we have is that there's 1 amp flowing through this 5 ohm resistor. And in this case, the question I'm going to ask is, what is Vs? And there's several ways you could approach this, and I like to start by writing out the answer to my question symbolically. So rather than start from information I know and then work towards the answer, I think sometimes it's good to start from what you don't know and then identify what you need. So looking at this circuit, I want Vs. And to me, it seems like if I'm ever going to learn Vs, I'm going to need knowledge about other voltages in this loop, and I'm probably going to want to apply a KVL here. So what I plan on doing, and for the record, you could approach these problems by trying to identify power. So one other way, because I know I always harp on KVL and KCL, but you could use power and the fact that it's conserved to try and identify certain voltages and currents. Like for example, if you knew how much power was consumed in all these elements, then you could work backwards and realize that, well, that same amount of power must be sourced over here, so then you could work and find the voltage that way. And maybe I'll do an example like that in the future, but this time I'm going to say I want to use KVL starting at this loop over here to try and figure out Vs. So I'm going to assign some labels here. I know that there's going to be some current flowing and a voltage across this resistor, so I'm going to pick a guess of the polarity here. And it's a pretty good guess because I can tell you the current is going to be flowing out of this source and through this resistor. So this will be the polarity across the resistance because I know this is a source and this is passive. So this is generating energy and this is consuming energy. And therefore the current that flows into this resistor will have to enter its positive terminal. So I'm just going to go ahead and label this Vx. And then I'm going to say there's a voltage here, this plus minus, and I'm going to call this Vp, P for parallel, because I'm recognizing that these 3 resistors are all going to share the same voltage. So I only have to label one place here, and I've covered the voltage for all 3 of these resistors. Okay, so the next thing is let's write out this KCL. So if I go around this loop, I'll say that as I step up, that's one polarity, and as I step down voltages, that's another polarity. So I'm going to say that they all sum to 0, or the step ups equal the step downs. So Vs, I'll say, equals Vx plus Vp. And that's the starting KCL. So then the question becomes, okay, if I can figure out Vx and Vp, then I'll have my answer. And I'm going to start with Vp because I'm realizing that I don't have any information about the current for this 5 ohm resistance here, so there's no way I can figure out its voltage right now. But Vp I actually already know because of some of the information that we've been given in the problem. So you notice that it gives us the current through this 5 ohm resistance. And so we know by Ohm's law that because V equals IR, the voltage across this resistor, which is also the voltage across the other resistors, must be, so Vp equals 1 amp times 5 ohms equals 5 volts. So we have Vp. And that's curious, right? Because even though this is just the current through this one resistor, it actually tells us the voltage across all three resistors, because whatever voltage appears across this resistor will be the same voltage across the other two. They're all shorted together by ideal conductors. So these nodes are all touching, okay? And there can be no voltage across them. So the voltage here is the voltage here all along this node. Now we know VP. Fantastic. And the next thing I want to do is figure out Vx. But to get Vx, I need the current through this resistor. So that would imply that I probably want to do a KCL to try and identify this current. But there's two currents I don't know yet. I don't know the currents through these resistors, but thankfully we have the information to figure that out because we now know the voltage Vp. And since we also know these resistances, we can trivially calculate those currents. So it just so happens that this 5 ohm resistor, this is the same resistance here that we already calculated the current for. And so because these two resistors have the same resistance and the same voltage across them, they must have the same current via Ohm's law. So we know that this is also a 1 amp current entering this 5 ohm resistance. And then applying Ohm's law one more time, we have 5 volts and 10 ohms here. And so because V equals IR, I equals V over R. So that's 5 over 10, or we have a half amp. So this is 1 amp, and 0.5 amps. And now we have all the information, and this KCL should be very obvious because we know that we have an amp, and another half amp all entering these resistors or leaving this node. So there must be some equal current entering the node, and the only path left is the path from this resistor. So it's clear then that the current coming in this direction, traveling through this resistor, is 2.5 amps. And that's great because now we know, based on this 5 ohm resistance, what Vx is. So Vx, remember V equals IR, so Vx equals 2.5 amps times 5 ohms, which is 12.5 volts. And now we essentially have our answer, and we can return to our original KVL expression and write out that Vs equals 12.5 plus Vp, which is 5, and therefore Vs equals 17.5 volts. And excellent, we've solved the problem. We've done it. That is the voltage Vs of the source. And now in this problem, again, I encourage you to step through and do the power calculations in each element to check our work here and verify, or rather increase your confidence that you've done your work correctly. But I'm not going to do it this time because I've done it in a few of the past videos, and I also want to have time to work in another quick circuit example. But again, I encourage you to do it. So let me go ahead and draw up the next circuit. Okay, here's our second circuit. And in this case, I've drawn something that's kind of mysterious or off-putting to beginner students or people that are just seeing this for the first time. A lot of times people get confused when you introduce multiple sources in the same circuit, or different sources that appear to conflict, or this is just kind of foreign territory that you know, a lot of times people aren't really sure what to do with this. So I'm going to talk about this. Don't worry, it's really easy as long as you just follow our definitions and rules for what these ideal sources are supposed to do and how they're supposed to behave. So I've drawn an ideal current source here, sourcing 2 amps. There is a 5 ohm resistor and some current IR going through that resistor. And then we have an ideal voltage source with 10 volts and this voltage polarity as indicated on the source. So I'm going to pose the question, 2 questions. 1, what is IR? And 2, we're going to find the power in each element, meaning what's the power either sourced or consumed in each element. The first question is actually very easy. It's completely trivial if you just look at our definitions. This is an ideal current source. And what this does is it forces the specified current, in this case 2 amps, to flow in the specified direction, no matter what is attached to it or the voltage across it, which means, as drawn here, because IR matches the same current direction as the source, it's in agreement polarity-wise. IR is just 2 amps. So that is really easy. IR equals 2 amps. So it doesn't matter that there's a resistor here. It doesn't matter that there's some other source in the circuit. You're probably thinking, well, what if this source is sourcing a current? But remember, voltage sources, of course they can source current, but that's not their job. Their job is to source a voltage. And now, depending on what you attach to that voltage source, there will be a different current, but the voltage won't change. This current source, on the other hand, this forces a specified current to flow. And now, usually, depending on what current flows, it'll interact with the circuit and cause some voltage to appear across it, but this current shouldn't change. So again, doesn't matter about all this other stuff. This IR is just 2 amps. That's what's being forced out of this ideal current source. Now the next question is, what is the power in each element? So let's start with the resistor, say, because that's a passive element, and it should be easy. First of all, we know that because the resistor is passive, it must be consuming power, and therefore we know that its voltage polarity is as follows, with the current entering the positive terminal. So VR is right here with this polarity, and we know VR via Ohm's law, so VR is just IR times R, and we know IR to be 2 amps, therefore VR equals 10 volts. And that's great. We didn't actually need to calculate the voltage to calculate the power. We could have done I squared R, and now we can also do V squared over R, or we can do I times V. But we're going to also need this voltage to solve the rest of the problem, so I thought I'd write that down first. Now let's just go ahead and say then the power in the resistor, and remember the PR will be IR times VR, P just equals IV. So PR is 2 amps times 10 volts equals 20 watts, and I'm writing this as a positive number because I know that there is power being consumed in the resistance. Now we're in an interesting position. We're going to tackle these two sources. And so I'm going to start with, let's say, the voltage source. Now this is interesting, and this is where things might get kind of confusing. But let's talk about this. So the voltage source, like I mentioned earlier in the problem, forces the specified voltage to appear across its terminals with the specified polarity, no matter what, right? But we also know that there's this current source forcing this current to flow in the specified direction, no matter what. So what we've encountered is this situation where IR is flowing through this resistor and continuing to flow, and then flowing into the voltage source, but it just so happens that IR is flowing into the positive terminal of the voltage source, which is really interesting, because what this means is that this voltage source is actually consuming power. So, and okay, that might throw you off a little bit, because you thought voltage sources source power, current sources source power, and well, they can and they do, except really what this is a voltage source. So there's nothing about the definition of a voltage source that forces it to source power. All it does is source voltage. And in many, many cases, It will therefore source power by virtue of what you attach to it, but it doesn't have to. You can see we've created this situation where we were able to attach certain elements that cause a current to flow into the positive terminal, and therefore, via all our definitions, this source is actually consuming power. And we know how much power by virtue of the fact that we know the current and the voltage here. So I'm going to go ahead and say, well, the current into the voltage source, let me go ahead and say IV, which is just equal to IR, is 2 amps, and then it's times the 10, well, and then I'll say the V of the voltage source equals 10 volts, as we know, and so the current in the voltage source times the voltage of the voltage source will now give us minus 20 watts. That's a total typo. I just got through saying how this is consuming power. This is a positive current with respect to our convention. The current is entering the positive terminal, so we say it's a positive current, and therefore this generates a positive power of 20 watts in the voltage source. Now the ideal current source, on the other hand, to calculate its power, we know automatically that this must be sourcing power because every other element in the circuit is consuming power, and we can verify that with KVL. So we see that we have a voltage drop here and another drop here, so there must be a step up here, and the total voltage across the current source must be equal to the drops across the other elements. So that's what I was saying before. The step up has to equal the total step up has to equal the total step down. So there's a step down of VR and then 10 volts and a step up of some voltage across here. And we can work this out because, and I'm going to call this VI, or the voltage across the current source. And with a KVL, I can say that VI therefore equals VR plus 10. And we know VR to be 10, so we have 20 volts across the current source. And now we've reached our convention for a power source. So we have current leaving the positive terminal of this current source, and therefore it really is sourcing power. So I'm going to say it's a negative current in the power calculation. So PI, or the power in, let me scoot that up, or the power in the current source equals II, or IR, so the current in the current source, times the voltage on the current source. And in this case, I'm going to say I here, or the current from the current source, I'm going to say negative with respect to our voltage polarity, just so that our convention works out with the fact that it sources power. And this is very common. That's what you do, is you usually say that the current is either positive or negative with respect to the voltage, depending on whether or not it's entering or leaving the positive node. And so we therefore have, because we have an IR of 2 amps, so we have a minus 2 amps here, times the 20 volts across it, which gives us a PI of minus 40 watts. And there you go. If you look at the fact that we have 20 watts being consumed in the resistor and another 20 watts being consumed in the voltage source, that makes up for the fact that we have 40 watts being sourced from the current source. So we've done it. We've answered the question posed in this problem. We found this current, which is essentially key because this is a series circuit here with one current flowing in this loop, and then we used that current along with the other information in the circuit to find the power in each element and verify that power is conserved between our sources and our passives. So on that note, I think I'm going to end the video here and probably continue with maybe 1 or 2 more videos on this type of circuit example with sources and resistors and power before moving on to the next set of big topics that I want to teach, and that's pertaining to specific circuit elements, different ways that we work with resistors and analyze resistors, and so on. So with that being said, I hope you enjoyed, and I hope this was helpful. And otherwise, have a great day.